Hi everyone, welcome to Docker Dieting, sizing up your Java images and containers. Just some quick background on me. My name is Melissa McKay. I am a developer. I have been for over 20 years, various positions all the way from intern to principal engineer, and in the last couple of years I started doing a lot more public speaking. I took a position with JFrog to become a developer advocate. Really enjoying that. Became a Java champion in that process and also a Docker captain. So I'm excited to share with you today a little bit of what I've learned. This is a typical story of someone relatively new to Java, certainly new to containerizing Java applications. And to be totally honest and transparent, much of this, especially the container side of things anyway, was my own journey. My background has been in Java for the most part, although it's rare that I meet a Java developer that isn't doing other things as well. However, that's been, my primary time in my career, and a lot of Spring Boot, that kind of stuff. So containers, however, were new to me. That was brand new. I was on a team. We were given this application that we decided we needed to containerize and get into a different type of infrastructure. And that's where I started. And my hope for today is that you get a better understanding and starting place than what I had back then. There will be plenty more to learn after this. I hope this presentation inspires you to do further research, of course, but my focus today is to give you a good foundation, especially for the beginners, at least where your Java apps in containers is concerned. There are a lot of things to worry about when you're working on a Java app. Most of the time, we're concentrating on performance and reliability, making sure that our application behaves as it's supposed to with an appropriate amount of memory and garbage collection behavior. Of course, we're also worried about build times and making sure that we have decent test coverage to catch bugs. But when you add Docker to your stack, you have a whole another set of issues to think about. And one of them is the size of your images. Why does size matter? This isn't really something we've worried about too much before. I mean, think about the size of our jar files or maybe our WAR files, maybe the server that we're standing our application up on, we might worry about that. But it turns out that there are actually a few very legitimate reasons to concern yourself with size of your containers and your images. And one of those is speed. When you think about continuous integration, you start to care about the speed of your builds. And depending exactly how your application is deployed, you will care even more about speed. And what I mean by speed in the context of Docker images is not necessarily the startup time of launching a container, although this is somewhat related. But what I'm talking about here is the time it takes to push and pull an image. It stands to reason that the bigger an image is, the longer it will take to send and receive to a registry. There are some details here around caching that make a difference as well, and we'll get into that later, but it's safe to say that smaller images will transmit over the wire quicker than larger images. This becomes important when you look to roll out updates to your services with minimal downtime, as well as automatic scaling of your services. You want these processes to be as fast as possible. Also, we all know what it feels like to suffer through slow build times during development. Regenerating and transmitting large image layers during a build after every commit can really slow down your build processes. Another reason to worry about size is security. It may be simplistic, but the less you have in there, the less number of packages or libraries containing vulnerabilities you have to worry about. The less chance you're going to come across those. Things that can cause you problems later by letting an attacker escape the confines of your container, or other risks like leaking private data. The idea is to reduce your attack surface area, and one way to do that is to simply reduce the size of your images altogether. Reduce the number of packages and libraries that you're installing to begin with. The last reason I'll talk about is money. And this is a big one, especially if you're using cloud architecture and paying for every bit of storage space. I'm going to age myself here, but I remember the days when I was charged for every text I sent or received from my cell phone. This is before, all the packages that we have today. But this is where we are at today with a lot of our cloud storage infrastructure and a lot of our bandwidth. Image sizes can easily get away from us, and it's better to be mindful up front about everything that we're packing into our images to begin with. A beginner can accept that size matters when it comes to creating Docker images, but how do you go about creating one with this in mind? A typical dev might go out to their favorite search engine and pull up several different examples. There are certainly more available now today than there were back when I started. The first thing that you'll likely find to do is to create a Dockerfile to begin with. This Dockerfile example comes from the Spring Boot Docker documentation, and it's going to seem like I'm picking on Spring Boot here, but I promise I'm not. Shown here is actually the first example that I stumbled across when I was learning. And hey, as far as real examples go, it's pretty good. You get the basics right away with a simple Dockerfile, just a few Docker commands to wrap your head around, and voila, a beautiful Docker image. You have to understand that when examples are provided online, the goal is usually to keep things as simple as possible to get you up and running as quickly as possible. After you've felt that success of just getting everything working, now your responsibility as a dev comes in to understand what you've done and improve on it. The more you dive in, the more you realize that what you started with might be naive and, in the worst case, certainly not suitable for production. I can't say strongly enough, any consequences of using this is going to be on you. Your job is much more than copy-paste. Now, there's enough I can talk about with just these few Dockerfile instructions to keep you busy for a while, but with just this basic info, you'll be creating better Dockerfiles and smaller, more performant images. The first thing to get your head around is how Docker layers work. Docker layers correspond to an instruction in the Dockerfile. In the case of the Dockerfile that we just looked at, there are just two instructions that result in a layer. So you can see that with each instruction, we are building more and more into our final image and understandably increasing that image size. Let's take a look at the first one closer, that from instruction. Docker images can be built based on existing images, and this is called the parent or base image. Technically, a parent image could have its own parent image that it's built from. A base image would be as far back as you can go. In fact, the first line in the Dockerfile for a base image would be from scratch. In this case, our image built from this Dockerfile would be based on the OpenJDK version 8 JDK Alpine. Let's take a look at that image right now using Dive. Dive is a tool that helps you to visualize the different layers in your Docker image. And I stumbled on this application when I was rooting around an image that I didn't have the original Dockerfile for. I was just trying to find a way to understand what all would be in that container that would be launched from this image without actually launching the container to begin with. Dive will pull the image you specify and give you an interface where you can compare changes between different layers. And, Docker Desktop is good for analysis too, but I really like how you can actually see the changes in the file system as you navigate the layers in Dive. And here's an example. Here I'm running Dive on our OpenJDK base image that we just looked at, and I can see that there are 3 layers in that image. These are the 3 rows on the top left. For each one, we have a set of information, including the size and what instruction created the layer. In this screenshot, we're sitting on the second layer. It's only 87 bytes, and it's a small change from the first layer. In this one, I've moved to the third layer. That's a difference of 99 megabytes, and I can see in this screenshot that some of the changes to the directory structure that would happen based on the result of this instruction. The yellow color indicates files and directories that have been modified, and the green color indicates files and directories that have been added. It's a little frustrating using Dive not to be able to scroll horizontally back and forth, but you can scroll up and down. But it serves my purpose well enough when figuring out where to look for inefficiencies and image bloat. All right, more on parent and base images. Let's talk about this a little more because it is important. Where is this image coming from? Is it from another internal team? Sometimes you might have like a platform team or something, and there could be some standard organization platform image that you've been asked to use. Another option is it from a public repo like Docker Hub? Is this open source or are there licensing considerations? Is this a well-known maintained image or is it an official Docker image? Official Docker images are a curated collection of images on Docker Hub, and these are expected to be maintained with updates as needed to address vulnerabilities, and they're transparent in how they're built. In fact, I'd like to show you what the Docker official images look like. Let's just chase one down so you can know where to find these in the future. I'm just going to go to my browser. I'm just going to search for Docker official images and see what comes up. What I'm looking for here is actually the primary source of truth for the Docker official images. This is the GitHub repo that backs them. And if you click on the GitHub repo, there's a whole set of images. They're all in this folder called library. And since we're looking at OpenJDK, let's go ahead and just scroll down and find the OpenJDK official images. Here we go. And when I open this file, I can see that there is a GitHub repo here. I'm going to copy that and open that in a separate page. And let's just see what this looks like. There's several versions here. Let's start with 11. Let's see what that one looks like. I can go into a JDK, and you can see there's all different versions here that I could choose from. Let me just go into the first one, Bullseye, and there's a Dockerfile. This is what I was looking for. If I pull this up, it gives me exactly how this image is created. The Bullseye OpenJDK 11 image. Now notice that this is actually built from another image. So I can go back through that same exercise that we just did. I can find the build packed ups image and look at the Bullseye SEM tag, and I should be able to find a Dockerfile there too. It's good to do this exercise, especially for any base image that you plan to be using for long term, just so you understand how it's being composed and where all these pieces and parts are coming from. All right, I'm gonna go back here. All right, we didn't talk about the last one. If it's not an official image, is this some random image? Just because it's hosted on Docker Hub does not mean that it's safe for you to use. Picking any old image out there without doing your due diligence researching it is similar to picking up a USB off the sidewalk and plugging it into your computer. You wouldn't want to do that, so please do not. All right, which should you choose? We kind of, looked around in the GitHub repo. We saw a lot of different names and versions and stuff. That can get pretty overwhelming. When you look at the available tags for Docker official images, you might just sit back and give up, and or maybe just pick the base image or the latest image, just because you don't know what else to do. Remember that tag latest is generally expected to point to the latest stable release, but you do need to do your research to figure out what that is the day that you pull it. You'll need to use the image digest to figure out what tag is pointed to what image. I would suggest not using latest just because it's better to know exactly what you're getting into. As far as the names go, you might see names like these in other images besides OpenJDK as well, but there's no mystery here once you realize what the names indicate. For a Java application, you could narrow your choices down by Java version, of course. Then, if you need to install additional packages on top of this image, you might need to pay attention to the Linux distribution that you're using. And by the way, Alpine is interesting. Alpine images are based off of the Alpine Linux project, which produces small images, especially for container usage. However, it uses a slimmer C library called Muscle that's different than what Debian uses, which is glibc or the GNU C library, and it requires an OpenJDK port. In fact, the port for Alpine is not even supported. It's not in a supported release by OpenJDK, and Alpine images are only released for early access OpenJDK version releases. They're not updated after they hit GA on a release. So that's good to know about these Alpine images. It might not be something you want to use or continue to use long term, especially since they're not maintained and updated. There are other options for parent images. You could make your own. Just choose another, Linux distro. You could get a base image for just Debian and then install your own JDK or JRE on there. You could also choose to use a distroless image. These are images that are slimmed down. They have the bare minimum that you would need to run an application. And they also do not include a shell. That's one way to minimize risk. You can't even exec into a running container. There's no shell to work with. I put a link here to the Google container tools. They have some distroless options for you. Note that it's just Debian 11 right now, and you can choose between Java 11 and 17. JLink is a utility that is bundled with OpenJDK 11. If you happen to be using, that version, you could make your own custom runtime. You would use that in conjunction with JDEPs to determine your module dependencies. So basically, you'd use JDEPs to figure out what modules your application relies on, and then you would build your runtime with only those modules. You can really significantly reduce the size of your Java container image if you do that. Whatever you choose, get an idea of how big they are after you've built the image. You'll notice right away that the JDK images are unsurprisingly bigger than the JRE images, and that slim images are smaller than the full images. But do that work to optimize and make sure that you test them well. You might find that a slim image won't work for your application requirements, and you need to use a full image instead. Let's go back to our original Dockerfile and look at the other layer we should be concerned about, the one resulting from that copy instruction. This is just copying a jar file in to have it available to run later. Given that we know this is a Spring Boot app, we can be reasonably certain that this is a fat jar, that it already has been built at some other point in the past in the process. Now, one more thing to understand about layers is that they allow us to benefit from Docker's caching mechanism. When a Docker image is rebuilt, if there are no changes detected in a layer, then the cached version of that layer will be used. But if there are changes in a layer, then there will be a cache bust, meaning that layer will have to be regenerated, and every subsequent layer must be regenerated. That's because each layer is just a diff of the previous layer, right? Knowing this, maybe it's time to do away with the fat jar, because every time your app changes at all, you will experience a cache bust. Here's another example of a Dockerfile courtesy of Spring Boot. First of all, at least this one considers the risks around running as root and creates a Spring user and then utilizes that user to run the application. But look at those 3 copy instructions. Instead of just copying one fat jar, the jar has been organized and split up into different layers. The first group, containing third-party libraries, is expected to change less often than the third group, which contains the class files for the code that would be in active development. So that makes sense, but let me explain how that actually benefits us. Let's say that you only need to change one class file and then deliver a release. This means that when you deploy, Docker would only require that layer that included the change, as well as subsequent layers, to be transmitted. The earlier layers would just come from cache. And since your change happened in a much later layer, you get a benefit from that cache. This helps with deployment, and it also helps with your CI builds. If you're building a new image for every single commit, and every commit involves regenerating large layers in your image, think about how much space this is taking up. This same strategy should be considered throughout your Dockerfile, not just your Java app portion. The least frequently changed files should be in layers earlier in the Dockerfile in order to prevent that high probability of cache busting. There are some other ways to get better cache behavior by breaking up the application into smaller layers. Starting with Spring Boot 2.3, the Spring Boot Maven or Gradle plugin will build jars that include layer information in the jar file. This information organizes and separates out the parts that are likely to change between builds. And a possible result that you can then use in your Dockerfile is what you see here, with dependencies that are separated from application contents in different directories. Another option is build packs. I put a link here for more info on that project. This is a project that was started by Pivotal and Heroku at the beginning of 2018. And that project actually joined the Cloud Native Computing Foundation later that year. Build packs can be used for other types of projects in addition to Java projects. It basically works by inspecting your code to figure out what kind of build is necessary, like finding a POM file, for example, and then building accordingly. Another option worth speaking to is the Jib plugin for Maven and Gradle. Jib actually skips the entire process of writing a Dockerfile altogether. It automatically determines the most efficient layering scheme based on your application organization, and then skips directly to creating an image. So worth taking a look at. I do want to talk about multi-stage builds really quickly. These actually weren't around when I started, so it was nice when Docker added these. Up until now, we've been learning some strategies in how to build a Dockerfile that produces small images and utilizes Docker cache effectively. The Dockerfile that we've looked at so far have all just copied in the build artifacts. And this feels a little bit incomplete. There's no way to tell where those artifacts are coming from or how they even came to be. And to get the benefit of the consistent environment that a container offers, it would be good to build from source in the Dockerfile. Might as well take advantage of that. In this file, there are two separate sections, both starting with a from instruction. I'll leave the actual build details. You can see I've deleted that part, whether that be Maven, Gradle, or other, and the cache improvements that we've already learned about for you. Do those as homework later. But you can see that with multi-stage builds, we can get the best of both worlds. The final image that results from this build will include only the second section of the Dockerfile. We can choose our preferred parent image and only include the build artifacts that we specify from the first section of the Dockerfile. Again, no matter what method you choose, make sure you evaluate it. Don't assume that you can predict the outcome by reading a blog or listening to a session like this. Make sure that you've actually built your application and you verify the results. For example, for reasons based on your application and just specifics to yours, sometimes images created from build packs, for example, are bigger than you might expect. Always verify that the results meet your expectations. At the very least, Go through Docker's Getting Started documentation to get familiar and comfortable with the commands you would use in a Dockerfile, and of course basics on how to assemble a Dockerfile. But then flex your Java muscles. And I really like the concepts that are explained in the Spring Boot Docker guides. I've included those links here. There are topics discussed that aren't specific to Spring Boot, so it's worth the read even if the examples are simple. The examples are simple enough to follow, and even if Spring Boot is not your framework of choice or what you're most familiar with, it's good content. The dive tool, I included a link here for that. It's great for analyzing those image layers, I just included here for reference. And I also included a JFrog knowledge base article that gives a good overview of the anatomy of a Docker image. And lastly, there's a link here to the official image documentation for OpenJDK. Take your time to read that. If you peruse through those, you'll learn a ton. One more thing, Swamp Up, which is JFrog's DevOps conference, is back. The agenda is live here. You can use this code MM25 to get 25% off on top of early bird pricing, which lasts through the end of the month. So keep that in mind if you want to learn more about DevOps, if you want to see me in person, and if you want to learn more about Docker containers as well. We've got some training and some sessions on that as well. Thank you very much. Thanks for listening. Please feel free to DM me with any questions or comments that you have. I hope you feel a little bit more confident now about building Docker images with your Java applications.